Hello everyone. It is our pleasure to present our work Counterfactual Attention Learning for Fine-Grained Visual Categorization and Re-Identification, which introduce a new framework to learn effective visual attention with counterfactual causality. Most existing methods learn the visual attention in a weakly supervised manner. In other words, the attention modules are simply supervised by the final loss function, without a powerful supervisory signal to guide the training process. This likelihood-based approach only explicitly supervises the final prediction, for example, whether the person is correctly identified, but ignores the causality between the prediction and attention. We cannot know whether the attention is correctly learned, whether it is useful. If most training samples of bird with tree trunk as background, then the attention model may be very likely to treat the tree trunk as a discriminative region. Besides, directly learning from data may encourage the model to only focus on some certain attributes of the objects instead of all attributes. Misleading and scattered attentions can still be observed from a well-trained attention model and potentially lead to the wrong predictions. To better understand this phenomenon, we analyze the statistics of both intrinsic attributes and external environments on the CUB dataset. Use ringed kingfisher as an example. We use the attributes provided by the CUB and manually collect the environment statistics. We see there are biases for both intrinsic attributes and external environments, which indicates either background and single part are not reliable clues for classification. Our method is designed for attention models for fine-grained visual recognition. Given an image and the corresponding CNN feature maps X, visual spatial attention model aims to discover the discriminative regions of the image and improve final prediction Y by explicitly incorporating structural knowledge of objects. This model can be reformulated using the language of causal graph. We can use nodes in the causal graph to represent variables in the attention model, including the CNN feature maps, or the input image X, the learned attention maps A and the final prediction Y. The link X to A represents that the attention model takes as input the CNN feature maps and produces corresponding attention maps. X, A, to Y indicates the feature maps and attention maps jointly determine the final prediction. Conventional likelihood methods optimize the attention by only supervising the final prediction Y and regard the model as a black box, which ignores how the learned attention maps affect the prediction. On the contrary, causal inference provides a tool to help us think out of the black box by analyzing the causalities between variables. Therefore, we propose to employ the causalities to measure the quality of the learned attention and then improve the model by encourage the network to produce more influential attention maps. By introducing the causal graph, we can analyze causalities by directly manipulate the values of several variables and see the effects. We propose to adopt counterfactual intervention to investigate the effects of the learned visual attention. The counterfactual intervention is achieved by an imaginary intervention altering the state of the variables assumed to be different. In our case, we conduct counterfactual intervention by imagining non-existent attention maps to replace the learned attention maps and keeping the feature maps X unchanged. The actual effect of the learned attention on the prediction can be represented by the difference between the observed prediction and its counterfactual alternative. We can simply improve the learning of attention masks by maximizing the actual effect. We assess the effectiveness of our proposed counterfactual attention learning method on several fine-grained visual recognition tasks including fine-grained image categorization, person re-identification and vehicle re-identification. The proposed counterfactual attention method can improve the strong attention model baseline. The improved attention model also outperforms all previous state-of-the-art methods on the three datasets. For the person re-identification task, we observed that our CAL methods achieve consistent improvement for different baselines on all benchmarks. With our strong attention model, we can achieve the state-of-the-art performance on Duke and MSMT datasets. Our method also achieves strong performance on vehicle re-identification datasets without using any extra labels in the training process. To have an intuitive understanding of our counterfactual attention learning method, we compare the attention maps of our models and the baselines models on CUB, cars and aircraft datasets. We see our method helps the attention models make correct predictions by reducing the misleading and scatter attentions. Besides, CAL encourages the model to focus on the main clues for classification and explore more discriminative regions. Thanks for watching. Our code is available at GitHub.